Let me dry off my hand. So. So let's see, are there any questions? I guess we might as well start then. You know how to start?
I just started it.
You just started it?
Yeah.
Okay, here, let me, you hungry?
Yeah.
Whoops. Let me flip sheet. Okay, so let's see. I think I'm going to depart a little bit from Weinberg's treatment in order to review some stuff that might be helpful. So the first topic is time-dependent perturbation theory. And the idea is that you, of course, write the Hamiltonian H as a part we understand, as a part we don't, and we pray that V is small. Now, the embarrassing thing about quantum field theory is that when we do this with standard, in the common field theories that people use, V is actually bigger than H0, so this is doomed to have problems, and of course it does. But what we do is we give, in the interaction picture, we give V the time dependence induced by H0. So we write this as e to the I H0t V e to the minus I H0t. Here we have units with, of course, H bar is 1, so it's not to clutter things up. The state, we alter the time dependence of the states, which would be e to the minus I Ht, by a corresponding H0. So we write this as e to the I H0t. So these are the way things vary in the interaction picture. And then we compute the time derivative of this, namely I d by dt psi of t. We can bring the H0 down where we want when we differentiate. It could come down here, it could come in the middle, it could come over here. But what we do is we bring it down in the middle, and so we have two i's, and that gives minus H0. But when we differentiate this one, we bring the H down to the left, and we have I times minus I, so that gives us H. And so this is just V. And instead of writing this as most simply by continuing, what I'm going to do is I'm going to throw in a minus I H0t and I H0t. These two are just unity. E to the minus I Ht psi. And so what this tells us is that I d by dt of psi t is, this is just V of t, psi t, because this thing here is psi at time t. So I'm reviewing the interaction picture. And now the solution to this equation is the time-ordered exponential. So the solution is simply time-ordered e to the minus I integral from 0 to t of b of t prime dt prime psi at, say, 0. And so now what we do is we expand this as 1 minus I integral b of t prime dt prime minus 1 over 2 factorial double integral t of b of t prime b of t double prime dt prime dt double prime and so forth. And these are both integrals 0 to t. Right, okay. So that's time-dependent perturbation theory. I think this is about the simplest way of describing it. And, well, let's see. I want to maybe ask you whether you wanted, how do you want to do this? Should I mean, one choice is to jump to the last equation we had on Thursday and continue, or to consider a theory that's a little bit simpler, cubic theory, and work that out first before going back to the...
Let's do the simpler theory first. Would be nice.
All right. This has the advantage, if we follow this, that I'll actually also derive the Feynman propagator for scalar fields. And I think that will be... Weinberg's way of doing it is, you know, as usual, it's great if you're as smart as Weinberg, but if you're not, then, or if you don't have enough time to puzzle out things, then when reading Weinberg, I sometimes get the, sometimes think about the black cloud. There was a now I'm wondering which way did I do? How do I? All right, I've gotten my notes screwed up. Hold on, let me just find out where I am here. So that's time dependent. That's Dyson. My goodness, did I print this? Oh, here we go. Okay, all right, so here's the simpler theory. This is a theory in which the action density is minus a half. Well, I almost lapsed into this GR notation, and I don't think we want that. So, I'm using letters from the middle of the alphabet to be space and all the others to be space-time. Minus m squared over 2 phi squared minus some coupling constant over 3 factorial phi cubed. So this is a phi cubed theory, and unfortunately this is not a realistic theory because the Hamiltonian would have a phi cubed term in it, and phi cubed terms can get very, very negative. So we have the usual the usual expression for the field. Phi of x is an integral p square root of 2 pi cubed 2p0 a of p e to the I p dot x plus a dagger of p e to the minus I p dot x. The theory that is somewhat more realistic is where phi cubed gets replaced by phi to the 4th, but then well, it's a more complicated theory. So the interaction Hamiltonian here is going to be g over 3 factorial an integral of phi cubed of x d cubed x. So that's our v of t, and we put that in here to generate Dyson's expansion like that. And now what we're interested in here is the scattering of two bosons of momentum p and k into final states p prime and k prime, and what we can let me just let's just see how this can go. P and K can go into one vertex, and then that vertex can produce P prime and K prime. So that's a Feynman diagram for this. There's another Feynman diagram, which is P like this. K prime can go off here. So let's see, do I have them? See, I don't know, maybe you guys know how to use LaTeX to draw Feynman diagrams. I found that to be hard to learn, and so I've never gotten around to getting good at it. All right, well let's just go on with what we're going to do. The amplitude is going to be P prime, K prime, and you have to do this in second order because you only have 3 fields to work with in first order, and you need to annihilate 2 particles and create 2 particles. And so the answer is -1 over 2 factorial integral t of v of p prime, v of t double prime, dt prime, dt double prime.
Kevin, can I ask a question?
Yeah.
Yeah, why in our v of t is there no time dependence?
Why what?
Why is there no time dependence? Why did the time dependence not show up?
Where?
In v of t, you just have phi cubed x?
Yeah, well, the t occurs in the time.
Oh, okay.
The field has the free field time dependence.
Sure. Oh, yeah, sorry.
No, that's good.
Forgetting that these things.
That's
work
an important
backwards.
question. Here.
Yeah.
Okay, so what is this? This is then minus g squared over 2 factorial, 3 factorial squared, p prime k prime integral t of phi cubed of x, phi cubed of y, d4 of x, d4 of y. So I've absorbed the t primes, t and t primes into the d4ths. And we skipped the treatment of scattering theory, but I think when you guys did quantum mechanics, you're familiar with the case where instead of integrating from 0 to t, we imagine that we have an infinite time interval for the scattering to take place, and we integrate over all time.
Should we have an initial state? On
Yes.
the item?
Otherwise, things would be kind of silly. So you get another candy. Open it. All right, so now the incoming particles, well, first of all, this can actually happen in 3 ways. And so I've only written two of them here, and that's why I hesitated. The third way is similar to this way. The difference is that if we have P and K here, we can have P prime here and P prime there. So there are 3 different diagrams.
Can I ask a question?
Yeah.
So last lecture you were using Hamiltonians, and now you're using this action density. What's the relation?
Okay, all right. First of all, always we split the Hamiltonian into a soluble part and an insoluble part.
Okay, I understand.
And always the thing is the insoluble part.
Yeah, what's this L?
L
Is
is the action density that defines the theory.
Okay.
From that theory, we get a Hamiltonian,
Okay.
and the Hamiltonian is actually an integral d cubed x, and it would be, in this case, it would be a half pi squared plus grad phi squared over 2 plus m squared over 2 pi squared plus g over 3 factorial phi cubed. This would be the Hamiltonian, where pi is the derivative of the action density with respect to phi dot, and that's just equal to phi dot itself. So this part, this is H0 plus an integral d cubed x, g over 3 factorial phi cubed. This part is quadratic, and you can solve it exactly. Did we ever do that?
I remember doing that.
So I never went through how it is that this is exactly soluble and so forth?
Oh, it's exactly soluble? No,
Yeah.
I don't.
Okay, all right. Well, that's because I've been following Weinberg, and I guess he regarded that as so obvious as to not to mention it. So this might be a good homework problem. If you actually, all right, let me assign it then as a homework problem. That'll be instructive. you take this field, and if you want, you can set the time equal to 0, or you can give it the free field time dependence. Whichever you want, you can take your choice. You take this thing and shove it into the free particle, quadratic part of the Hamiltonian. And then what do you have? You have a d cubed x, you have d cubed p, but because it's quadratic, you have a d cubed p prime. But the p's, well, you also have x's. The x's occur in these exponentials. It's the same x because the field's at the same point. Consequently, the x integration gives you a delta function. When you're done with the delta function, you get various things that cancel, and you're left with something. The thing that you're left with is the Hamiltonian. And what you can do is you can take that Hamiltonian and then normally order it. And what you find, so let me give you the answer. The answer will be an integral. Now, the problem is I don't know if I'm going to get the factors exactly right. But I think this is the answer. D cubed p, p0, a dagger of p, a of p, plus a constant, which is, which I'll just write as capital lambda, and, hold on, I left something out. In fact, yeah, let me give you the whole thing. There. That's the Hamiltonian if you do it.
Without the cube term.
Without the what?
Without the cube term.
Without the what?
Without the cube term? Because you have the cube term in there, and then you just said that.
Oh, right. This is just H0, sorry.
And also, so last lecture when we were picking some Hamiltonian, it was like different fields that were in there.
Yeah.
That was all the same field.
The problem I was working on for you on Thursday was a more complicated theory in which fermions are interacting with bosons.
Okay. Is this like they're all the same field?
This is a case, and that theory was cubic, but it was quadratic in fermions, and the third field was, in other words, in that theory, V was psi dagger psi phi times some coupling constant. Now, so what I asked you at the beginning of the lecture is, you want me to go on with that one, or would you rather that I do something simpler first? And I think, and you picked doing something simple first, and I think that was a better choice. So now, as a homework problem that won't be due until Thursday of next week, take this thing, put the field into it, and show that you get this. Notice that this extra term, 1/2 d cubed p p0, is badly divergent. It's infinity, it's the fourth, it's infinity to the fourth power.
It's big.
And so that shows you that there's something wrong with quantum field theory even when you can solve the theory. So it's not just that the perturbative expansion expands the Hamiltonian until something that's simple and something that is not only not small, but is bigger than this term. That leads to different problems.
So is normally ordering just to get rid of these infinities, or is there another reason why we should?
Normal ordering is always when you put the creation operator to the left of the annihilation.
Well, yeah, you only get the 1/2 though because you commute an A with an A dagger.
We got the 1/2 because of that.
Yeah, and so if you normally ordered beforehand,
Yeah.
you don't get divergence,
And
right? So is that like the reason for normal ordering? So is that like the reason why we
normally order because you want something such that, well, if you had it in some other order, you see, the point is that this structure annihilates the vacuum, so you get a 0. Then you get something that you don't want. So what typically people do is they say, well, this is a problem for another day, and we're just going to subtract this constant from the Hamiltonian. Who cares? And during some decades, there was a huge divorce between particle physics and general relativity and gravity. And in fact, I think that the part of that was that the particle physicists were jealous of the fact that all the public attention went to Einstein. And so they tried to, well, all right, never mind the sociology.
So they built the LHC. But then LIGO stole all the press anyways, like 2 years ago.
No, I'm talking about the 30s, the 40s, the 50s,
But it's still happening today. I mean, the gravitational wave people just stole the Higgs boson.
Well, yeah, there's still a huge gap, but there's much less of a gap today than there used to be. Today, most particle physicists feel obligated to learn something about general relativity. Although I think some relativists still don't bother to learn anything about particle physics. Okay, so let's leave it at that for the moment, the homework problem. All right, so where were we? So what I was saying was there are then 3 ways in which the 2 initial particles, P and K, can become final state particles. And but they all occur in second order, so there are many terms here. The simplest one is for 2 of the incoming particles to be deleted at one vertex and the other 2 created at another vertex. That's the simplest one. It's the one that I did explicitly. And so this thing is A1, and first of all, the vertex at which the 2 particles are deleted, maybe you should turn it around.
Oh, yeah.
The 2 particles can be deleted either at X or at Y, and I chose them to be deleted at Y. Okay. Then, one of the fields is left over from this vertex, and one of the fields is left over from this vertex. There are 3 choices for which of the 3 fields. So that means you get 2 factors of 3. You also have a factor of 2 according to whether the 2 particles are annihilated at X, at Y, or at X. So when you're done with that, what you have is minus G squared over 4. Vacuum A of K prime, A of P prime. This creates the final state. Integral, and now we have D cubed D double prime, D cubed K double prime, D cubed P triple prime, D cubed K triple prime. We're dividing by, we've got 4 fields contributing here, so we have 2 pi to the 6th. And then we have a square root of 2p double prime 0, 2p triple prime 0, 2k double prime 0, 2k triple prime 0. And then we have a dagger of P triple prime, a dagger of K triple prime, and then we have e to the minus I P triple prime plus K triple prime dot X, because this is, they created it at X. Then we have the time-ordered product of the two leftover fields. And then we have the factors from annihilation, which are e to the I P double prime plus K double prime dot Y. And then d fourth X, d fourth Y, and the initials say a dagger of P, a dagger of K. Okay, so that's the amplitude for this diagram. P, K, P prime, K prime, and Y, X, if we're still doing really space-time diagrams. That's how that works. So now the creation operators on the annihilation operators and the let's see, I think I left out two annihilation operators. Yes, I left out two annihilation operators. A of P double prime, A of K double prime, and this guy can annihilate this one, it can delete this one, or it can delete that one. So there's a factor of 2. And moreover, this one can pair with that one, or it can pair with this one. That's another factor of 2. So this 4 goes away, and what we have then is minus g squared integral d fourth x d fourth y 2 pi to the 6th, and then this square root, and well, maybe I'll pull out the 2's. So there were 4 2's, and so that means when you pull through the square root, you get 2 2's, which is 4. So you have 4 square root, and then I'm just going to write it as the product of the energies. Of all the final and initial and final particles. Question?
Can I ask where the creation operator in between comes from?
These creation operators came from 2 of the fields at vertex X. And then these annihilation operators came from 2 fields at vertex Y. And then the commutation relations toss out delta functions. That is to say, A of K, a dagger of P is delta Q of K minus P. This is because these are scalar, real scalar bosons for simplicity. And so this whole thing then is e to the I P plus K dot Y minus I P prime plus K prime dot X. And what's left is just a vacuum state on the left and a time-ordered product in the middle. Now, so let's see. The other two diagrams are pretty similar. It's just that you take one of the fields at X and use it. In other words, here we had two of the fields at Y we used to delete the initial state particles. What you could do is you could have one of them delete an initial state particle, the other one create a final state particle, and then over here you could have one of the fields delete an initial state particle and one of the fields create a final state particle. And that would give you these other two diagrams where you have pk and you have P prime, K prime, or K prime, P prime, and this is P, and this one is K. So if you want, I could do them explicitly on the board. Otherwise, we can just go on and analyze this term, which is the Feynman propagator.
Yeah, can you explain again where all the terms went? So I know you, so you commuted the A daggers that you have there through the A's. So you have the, like the A dagger P triple prime through all of the like A of P double primes, right? And that gave you a bunch of delta functions.
Well,
Use that to
no,
introduce-
it's A dagger P triple prime is going to.
Oh yeah, because you went
It's gonna do
annihilation
that.
on the left. Yeah, okay,
Right.
okay.
And these guys are going to do this.
Yeah. Okay. I see. I see. Okay. But then do you need to commute? Then you furthermore commute the A dagger of P's through the remaining A's that are up here?
Well, both of these,
Yeah, you.
oh
no, but then you
both
can
of these,
see-
the ones on these two pair with these two,
Yeah.
and then these two pair with these two.
Okay. Yeah, okay, yeah, because in the term with the delta function you no longer have the A's.
Yeah,
A
because
daggers,
as
yeah.
this comes
I
through
see.
here, this one commuting with that, you get a delta function, and then you get a term where it's sitting next to this one, and you still have that one with this one. Yeah.
So why we pay attention to this special term?
Excuse me?
Why we pay attention to this special term?
To what special term?
Since this is not the only combination to make it non-zero.
Well, all right, maybe I should just do this explicitly. So what do we have here? We have A of P double prime, A of K double prime, and we have A dagger of P, A dagger of K, vacuum, right? Okay? All right, so what is this? This is equal to A of P double prime times A dagger of P, A of K double prime, plus delta of P minus K double prime, A dagger of K, 0, okay? Now, what is that? Well, the delta function term you have delta function, and then you have A of P double prime, A dagger of K. Well, that just gives you another delta function times the vacuum, because this times that, if you commute the A through, it hits the vacuum and you get 0. The other term is this term, A dagger. And now, let me see what I've got here. So let me just get things straight here. I've done this with that, and we've got that, and I've done this term. And so what we've got left is plus A of P double prime, a dagger of P, A of K double prime, a dagger of K vacuum. That's what we've got left. Now, this one, with that one, gives you a delta function plus 0, because if the A goes through, you get 0. So that gives you delta of K double prime minus K times the vacuum. But then we have this term multiplying it, and this is, if the A goes through, you get 0. If it doesn't, you get a delta function. So this is delta of P double prime minus P. So this gives you two delta functions like that. Is that all right?
What?
Is that okay?
I couldn't really see anything. A lot of things blocking me. I don't know.
Because the heads are in the way?
My head's and you were standing in front of it. Yeah. I can work it out tonight.
Well, you can come and sit there. You don't have to sit in that chair.
I like this chair. I asked like a bunch of questions. I didn't get any game.
Well, if you want to ask questions, go ahead.
What? No, I didn't get any candy.
Huh?
I asked a bunch, I didn't get any candy.
Oh, shit. All right. Yeah.
Is there any root propagator in the solutions become suppose if this dagger, if this is creation, this is annihilation, would that cause any problem?
I still don't understand what you said. These guys multiply this, and these two things came from two fields at X.
If this is creation operator,
These are annihilation operators.
if this is creation operator, would that cause any problem? If this is creation,
Okay, all right, okay. Right, all right. Good question, good question. This one, if you had these two be creation operators, that would correspond to the diagram where X and Y get interchanged. You see, there is another diagram, which is so if these two were creation operators at Y, then Y would have two creation operators and X two annihilation operators. And these would be two annihilation operators. And this diagram and that diagram are numerically the same, and that was the factor of 2 that I canceled at the very beginning. That's the 2 factorial.
Does
So-
anyone ever write all these terms out?
What?
Does anyone ever work out all the terms?
Well, they all work
Like,
out.
well, no, yeah, I'm just saying, like expanding out all the terms and explicitly saying.
Well, I suppose that the first time you do something like this, maybe it would be good to write them all down.
Yeah.
Now, if you want, I'll do on the board, say, one of these diagrams. You want me to do that?
That would actually be nice, yeah. I would
You think it'd be
I don't
good?
know If,
Yeah, maybe
if
just like
everyone
one
else
more
would
row.
like it. Yeah.
All right, let's
I
do
feel like that'd
that.
be helpful. You can
Okay,
actually
so-
see all the terms working.
So what is A2? A2 then, well, what we said in the very beginning is that we're going to have, let us say, the meson with momentum p, the boson with momentum p, we're going to have annihilated at y. Let's say we're going to do that. So the thing looks like this. P, y, but now instead of the other one being annihilated there, here we have, let us say, p prime. K comes in, k prime, and that's x. Okay. Now you can have the same thing with x and y interchange. That's the factor of 2. But I'm doing this one. Okay, so what will this look like? It'll be minus g squared over 3 factorial squared. And then it'll be, of course, p prime, k prime. And it'll be this same business of integral, I'll just write it as d cubed of all the momentum. And it'll once again be 2 pi to the 6th square root of 16 times the product of the energies. But now, we're going to have one field here is going to have an A of P, or if you want, what we've got is time-ordered product of these fields. So we're going to have a phi plus of y that's going to take out the P field. And there's another phi. It's going to be a phi minus at y, and that's going to be the P prime field, the P prime particle. It's going to add the P prime particle. And then there's the leftover phi of y. And then over here, you have a phi plus of x. And that's going to do the k particle. You have a phi minus that's going to do the k prime particle. And then you have a leftover field phi of x. Okay, I think that I've got everything there. So now, this
So the leftover fields here are representative of the vertices. Like the leftover fields that you have are representative of the vertices?
the leftover fields are
Yeah.
the ones that are going, the leftover fields are like the ones that stay in the time-ordered product.
Yeah. So it's like whenever, I mean, you need to put that there because of the vertex that's there, or
I
mean, I get why you have like a phi plus a p, because a p's coming in, you want to annihilate it, and a p prime comes out, so that's why you have a phi minus a p prime.
yeah.
But then you have this phi y.
That's the
Yeah.
field that's left over, doesn't do anything, just sits in the time-ordered product.
Okay. Sure. And you're like, oh, okay, I shouldn't think anything about if this field's going to create anything.
Well, I'm going to get to that when I do the Feynman
Okay.
propagator.
I see.
What?
Suppose we know see a Feynman diagram. We have expansion that correspond to each other. So
Yeah.
if we look at the expansion, how to draw the Feynman diagram?
Well, you see, in Dyson's expansion, there are, as you pointed out, in fact, many, many terms. You first draw the Feynman diagram, and then you pick out those terms in the Dyson expansion that correspond to your Feynman diagram.
So if we have a Feynman diagram, how to write the?
Here, all right, hold on. Let me. I meant to. I like to have light. Sam is either hungry or he has a question. I'm not sure which.
It's okay. But I just, like, physically, what does this Feynman diagram mean? Because it's like, usually it's like, you know, you'd have these two electrons coming in, and that middle line would be like a photon that was like, there was scattering or something.
Well,
so what's this
okay,
middle line?
in this case, it's two bosons coming in.
Yeah.
They exchange a boson,
And it's all the same field.
and then
so
they go,
it's-
and then two bosons go out.
Okay, so they exchange, and it's like two photons, and then maybe they interact.
All right,
with
it'd
each
be
other
like two
somehow.
photons coming in, two photons going out, and they exchange a photon.
Okay.
But of course, photons don't scatter that way.
Yeah. Okay. Is there anything that scatters that way, like with itself?
Well, in this toy theory, the neutral particle scatters that way.
Okay.
And in the theory we were talking about last week, we had a fermion coming in, a fermion going out, and then a boson going across.
Yeah. Well, I guess are there any like physical theories that are real, where particles are like the thing that's being exchanged that's causing the scattering is the same.
Yeah, and right, because for example, if we go back to this, what do we have left? We have this phi of x, phi of y, okay? Now, if this was 0, the whole amplitude would be 0. Now, I already said this is P, and that's P prime, and this is the leftover one. So that basically blows away the 3 factorial squared. Because there are 3 choices for which one gets left behind here, which one gets left behind here, and another 3. And then which of these 2 does the deleting, and which of the 2 does the adding is another factor of 2. So this is gone, and we just have minus g squared. And so now if we write this out, this is going to give a gazillion delta functions. And what are we going to have left? We're going to have...
Wait a second, I have a question about what you just said. So you're saying, oh, which one of these does the deleting, which one of these does the adding, but you have 5 plus, right? And 5 plus...
I chose, yeah, but I could have, I
one.
could have made that, I could have picked the phi minus from that field.
Okay. Okay, so you're saying that you shouldn't have had the 3 factorial squared to begin with if you were going to write this down.
Yeah.
Okay, sure.
All right, so you get another candy also.
Sure.
Waiting. Oh. Okay. So, I mean, what you could have done, you see, was write both of these as phi, and write each phi as phi plus plus phi minus, and then you would have canceled 2 extra 2's. Okay, but what do you know happens here? All the annihilation operators contribute delta functions. And get rid of these initial and final state particles. What you have left is going to be d4th x, d4th y, and I forgot that we have d4th x, d4th y. I left that out. Then what we have is 2 pi to the 6th a 4 from there, square root of the e's, product of the energies. And then we're going to have e to the I y p minus p prime, because we're going to get a plus phase, we're going to get ipy from this, minus ip prime y from that. And then we're going to have e to the ix, and we're going to have k minus k prime from these guys. What's left over is vacuum time ordered product phi of x, phi of y. So now you can compare these two expressions, and the two expressions are completely the same except for the signs in the exponential, whether the p's go with the x, whether the whether p goes with x or y, whether p prime goes with x or y, whether there's a plus sign or a minus sign, and so forth. So that's that diagram, and consequently we can write down immediately what the other diagram is. If we put a y there and a p here and a k here, then we can make this one p and this one k prime. And so this would be ditto, but now what's different? At y, we're going to have p, we would have e to the I y, p minus k prime, e to the I x, and it would be k minus p prime. And a k minus p prime, yeah, that's fine. Okay. So that's how you would get, that would be the third one. So this would be A3, this equal to A2, and you add all three of them together. Now, let's focus now on Feynman's propagator for a real scalar permission field. These notes are online, although the notes are not in the same order. The notes are, the sequence that I've done in class is 1, 4, 3, 2, and I'm not going to get to 2, so I'm going to go to 3 now. 3 then is the Feynman propagator. And I do this Feynman propagator in 4 pages, whereas Weinberg does it, I think, in 1 or 2 lines. And because he's doing the Feynman propagator for particles of arbitrary spin. I'm just doing spin 0. We can do arbitrary spin next Tuesday. You realize Thursday is a holiday. Mm-hmm. Thursday and Friday are spring break. Okay, well, the Feynman propagator is the Green's function for this differential operator, which is to say, it's a solution of this differential equation. That's the Feynman propagator. But there are many Green's functions that solve this differential equation and give you a delta function. The Feynman propagator is one that has particular boundary conditions. Yes.
You want me to ask a question?
Yes, go ahead. What's the question?
Oh, I mean, just does this like deltas? See, the symbol used for the Green's function looked like a symbol you've used in the past. I was wondering if there's any connection.
Green's functions are always differential operator acting on Green's
I'm
functions
talking-
gives
no,
you
no.
a delta
I
function.
know that, I'm talking about the symbol, that triangle. You've used that in the past to mean something else. I was wondering if there's any.
Oh, yes. Well, but they're related. This is just a particular
Okay.
delta f of x is a particular Green's function.
Okay, so it's not just a general.
This is Feynman's Green function. It's Feynman's propagator. Well, there's always this factor, extra factor of minus I, and but this is the Green's function for that differentiate. So capital delta is the Green's function. Well, we know what this is, namely this is just default q e to the I q dot x over 2 pi to the 4th. So it's obvious what delta from f is, namely delta of f, this can just be n squared minus box. So what we need is we need this. But then we just have to compensate for that. And the way we compensate for that is we just divide by m squared. And then what happens when box hits this? Well, when box hits that, it pulls down a q squared. And it turns out it brings down a q squared with 2 i's, which cancel the minus sign. So this is m squared plus q squared. So basically, this is a possible Green's function for this differential operator. And what Feynman did was he added in a minus I epsilon. And the minus I epsilon is to put in suitable boundary conditions so that it gives you this expression. Okay, now let's see how that works. First of all, q squared plus m squared is equal minus I epsilon. What is it? Well, it's q dot q minus q0 squared plus m squared minus I epsilon. By the way, let me ask you guys a notational question. Do you prefer, for the vector part of x, do you prefer that, or do you prefer x in bold face like that?
The arrow.
Like the arrow.
You prefer the arrow? Aha. That's very interesting. I also like the arrow for 2 reasons. The first reason is that if you have a mixture of 4 vectors and 3 vectors on a page, the thing looks ugly because you have a lot of these dark splotches if you use boldface to represent 3 vectors. The other reason I don't like the boldface is that it was introduced by Elsevier, a company that I detest. We still, by the way, can't get Elsevier articles from before, I think, 2000, or is it 1990? I'm not sure which it is, but the university can't afford to subscribe to that. Yeah.
So Dr. Finley, he uses an arrow if it's a 3 vector, and then he uses a tilde if it's a 4 vector, and then it's really easy to tell them apart.
Yeah, well, I think that's completely crazy.
You think that's completely crazy?
Yeah.
I mean, Dr. Finley, he's a pretty smart cookie, though.
Yeah, well,
They named the library after him.
yeah. You sure he doesn't just mean the tilde for a form?
I think he uses both.
No,
he uses.
All right.
Not tilde.
Yeah.
Oh, he uses hats for forms?
Yeah.
Tilde is.
Yeah, if it's like a tangent vector, I think it's the above tilde.
All right, look. I'm going to use arrows then. Anyway, I don't have boldface chalk. But I'm wondering about the second edition, and I'm wondering whether I should use boldface or arrows. If you guys prefer arrows, I'm going to go with arrows then.
Arrows. Because if it's a bad printer, then you can't tell the difference between.
Say it again?
If it's printed for some reason and the print is bad, you can't tell the difference between bold and not bold.
That's very interesting. Thank you. I just find them ugly. Let's see, who's okay, well, let's get the show on the road here. We can write this approximately as q minus I epsilon prime minus q0 e sub q minus I epsilon prime plus q0 plus epsilon prime squared. Now, why did I go to epsilon prime? Well, the point here is that when you multiply this out, you see, the term that's linear in epsilon prime, let us say, is what? Well, it's minus I epsilon prime times EQ plus Q0. And then this one is EQ minus Q0 so it's minus I epsilon prime times 2EQ. But EQ is the positive square root of n squared plus q vector squared. Epsilon prime squared is negligible because it's the square of an infinitesimal quantity. And the rule for what is epsilon prime is 2EQ epsilon prime is equal to epsilon. So that's the idea here. And what's important here is just that we've got some small imaginary part here. So this integral here for Feynman's delta f, so Feynman's delta f is going to be d fourth q over 2 pi to the fourth p I q dot x divided by this denominator here. And in particular, the q0 part of the integral, this means that I of q will be minus the integral of 0 to minus infinity plus infinity dq0 over 2 pi e to the minus I q0 x0. And this is going to be 1 over q0 minus EQ minus I epsilon q0 minus EQ plus I epsilon. So now if you multiply all that out, what you see is you've got a plus I epsilon here. And a minus I epsilon there, and this is just these factors here, Q0. So the second factors are those, this is this factor, and I pulled out an overall minus sign. Okay, so what is this? This is an integral along the real axis. And we have poles. Where are the poles? Well, I have a diagram for you here. There's a pole here at EQ minus I epsilon, and a pole here at EQ plus I epsilon.
Okay. Before it was a 4-dimensional integral, now it's a 1-dimensional.
Yeah. I'm doing the time integral. I'm doing the Q0 integral. We'll do the.
I see.
So the Q0 integral is the one that appears to me to be the most natural one to do. Okay. Now, as with any analytic function integral here, it depends upon what this external variable x0 is, whether it's positive or negative. Okay, suppose that x0 is positive. Okay, in that case, if x0 is positive, then we want to add a ghost contour like this. We can add this contour in the lower half plane, because now if we have Q0 is minus I times a huge number, this will be minus a huge number times something positive, 0. So you can add this ghost contour and nothing happens. And what do you get? Well, what you get then is you just pick up this pole and you get 2 pi I. So the 2 pi's cancel, so you get minus I times whatever this is, which would be e to the minus I x0, and q0 is eq, apart from the I epsilon, which you can ignore at that point. And this is this term, and so what we've got then is Q0 is 2EQ. And because this is clockwise rather than counterclockwise, we get a minus sign. Okay, so in the notes, this is equation 40. That's what you get for x0 positive. For x0 negative, then we add a ghost contour like this, and now we are going counterclockwise, and notice I did something dumb here. I didn't go around the pole. So obviously, we want to go like that. Okay, and now what we do is we're picking up the pole at minus EQ plus I epsilon, and so this is equal to minus I e to the minus I x0. Q0 now is EQ, and we're picking up, no, Q0 is minus EQ, so that's a plus sign. And we have minus 2EQ in the denominator, and so altogether this is I e to the I x0 EQ over 2 EQ, and yes, that's equation 41. Okay. So that's what we get for the integrals over Q0. And so we can rewrite this. Well, we're sort of running out of time. This is, it's another page and 2/3. Do you want me to
I just wanted to
do it, or shall we quit and come back to this point on Tuesday?
You can just come back to this
Go
one.
back to it. on
Tuesday?
Yeah.
Okay. All right, let me just write down on this blackboard, though, the final result, since I think I owe you another one, I think. I don't know who it was who asked that question. But let me,
Whoa. Look, they made the bag too short.
huh?
Look at that. The bag's shorter than the rest. It's like a defect.
Fuck.
It's cool, right?
All right.
Good luck.
Look at that. They're usually
Okay, but let me try to get this straight. All right, so what we have then is minus I of q. This is this integral. I called I of q this integral with, for some reason, an overall minus sign. And the answer is that minus I times I of q is 1 over 2e sub q times theta of x0 e to the minus I eq x0 plus theta of minus x0 e to the I eq x0. All right, so we can stop at this point. This basically is the key point in the derivation of the Feynman propagator. The remaining part of the derivation is downhill. All right, so we can, are there any other questions? All right, we could turn this thing off then.